Hi, my name is Adonis and I'm here to present the paper Remote Measurements of Lightning Return Stroke Peak Currents based on Electric and Acoustic Signals in the International Conference on Lightning Protection and International Symposium on Lightning Protection. Let's start with the introduction. Well, perhaps the lightning peak current is the most useful parameter from lightning because you can use this parameter, for example, to develop standards related to lightning protection of a variety of systems, including power systems and lightning protections for houses for human beings. However, the direct measurement of lightning peak current is not an easy task. We can measure the lightning peak currents, the direct measurements of lightning peak currents using instrumented towers, in which we have different sensors installed in the towers, for example, Rogowski coils, oscilloscopes, and so on. And I show you two names of examples of instrument towers around the world. The Santos Tower in Switzerland and Morro do Cachimbo Station in Brazil. We can also have the direct measurement of lightning peak currents using the rocket and wire technique in the rocket-triggered lightning facilities. For example, the International Center for Lightning Research and Testing in Cambridge, Florida, or the Guangdong Comprehensive Observing Experiment on Lightning Discharges in Guangdong, China. However, because of the random lightning occurrence and the high costs involved instrument towers and rocket-triggered lightning facilities, there are a limited amount of data from these experiments. The use of field-to-current conversion equation is an alternative to obtain lightning peak current with a large sample of a relatively short period. The field-to-current conversion procedure uses data from direct measurements of lightning peak currents that we can use the direct measurements from instrument towers or rocket-triggered lightning facilities and measurements of electric fields. Here I have a schematic of the direct measurement of peak current using rocket-triggered lightning and the electric field. So the field-to-current conversion equations that we are going to use in this paper are two. One provided by Hakov and co-authors, and another one by Malik and co-authors. So in order to have the peak current, we need the distance between the lightning channel and the electric field measurement station and the electric field peak. Well, one of the easiest approach to estimate the distance strike is the so-called time to thunder method. Well, this method assumes that the electromagnetic waves travels faster than the sound waves. So here in red, we have a schematic, a draw for the electromagnetic waves that goes at the speed of lightning, and the sound wave that go very slow if we compare with the speed of light. Well, using this formula where d is the distance to the lightning channel, vt is the average speed of the sound wave, and t is the delay between see the flash and hear the thunder, we can estimate the strike distance, or the distance between the lightning channel and our sensor. Well, in this paper, our eyes will be a flat plate antenna that will record the electromagnetic fields, and our ears will be a microphone with our audio preamplifier. Now moving to the methodology, I show the full schematics of our instrumentation that's composed by a flat plate antenna, a wide band flat plate antenna, uh, audio preamplifier, a PIC scope, a laptop, a microcontroller, and a GPS module. Well, when the electric field passes the threshold of the trigger circuit, I get a precise timestamp from the GPS module, and I also start to record both the sound wave and the electric field at the same time. And then I can measure the delay between the electric field and the sound wave. Here I have some examples for a lightning that occurred at 1.3 kilometers from our station, according to the time to thunder method, and according to the Earth Network's global lightning network at 1.7 kilometers. So our data set is composed of 54 negative call-to-ground flashes containing 132 strokes. Here I have another example with a more distant flash. And here the example showing how we measured the electric field peak. Now moving to the results and discussion, I will show first the distance estimation. So here A is the distance, the scatter plot of distance estimation using our method versus the distance reported by the Earth Network Global Lightning Network. So A is for first strokes, EB is for subsequent strokes. Well, in this figure, in the following scatter plots, the solid blue line is the best fit to the data, and the solid red line represents the ideal situation when the distance from the TTM method is the same as distance from EN/GLN. So the scatter, the figure B is more scattered than the figure A, that's for first stroke, maybe because we assume that all subsequent strokes occurred at the same distance as the first stroke, because from the point of view of the time to thunder method, all strokes occurred at the same time. So we cannot distinguish between the distance for first strokes and subsequent strokes. Now I show the arrows, the histograms for arrows when we compare the distance of our method and the distance reported by EN/GLN. Well, the average arrows for subsequent strokes is higher than for first strokes because what I mentioned before. Now let's move for the results for peak current estimation. Now I show the peak current estimation using Rakov and Coulter's equations and for Malik and Coulter's equation. So here we have the scatter plot for first strokes, and here the arrows of the estimations of peak currents. Now moving for subsequent strokes, that we can see that more scattered than for first strokes. And here the errors. Well, now I show the statistics on peak current magnitudes. So it's despite the very high scatter when we compare single events of Earth networks and our approach, when we see the statistics in terms of arithmetic mean or geometric mean, the results are very close from each other. For example, the average of first stroke peak currents using our methodology and Malik fidget current conversion equation is 32.2 kiloamps, and for Earth networks is 31.7. So very close from each other. The same for subsequent strokes. Well, in summary, in this work we infer peak currents from many events, 34 first strokes and 55 subsequent strokes. It's very important to note that because of the high variety of return stroke key parameters, such as return stroke speed, is a challenge in infer peak current for remote field for a single event. So that's why when we compare the results for single events, we can find very high errors. However, the use of statistical estimation in terms of mean values and standard deviation is valid for further analysis. And the GM, the geometric mean of the first stroke peak current, estimated with Malik and co-authors empirical formula, is 28.7 kiloamps versus 25.1 kiloamps for peak current reported by ENGLN. So very close. And the same, but for subsequent strokes, 13.6 versus 13.4, very, very close. Well, these results are closer to standard values. And the main purpose of this work is show that this methodology can be applied in regions in which we don't have lightning location data, or we don't have lightning location data with reported peak current. Well, the author would like to thank Earth Networks for providing ENGLN data, and a special thanks goes to the two reviewers that provided useful comments on the paper. Thank you very much for your attention, and if you have any further question, please email me.